Can you hear me at the back? Thank you. So thanks, Ajit, for the introduction. Just to sort of say that when people like me come to give a particular talk, the most important thing is that there is the next generation which has taken things forward. Because if they don't take things forward, there is no point in talking about history. So I would like to sort of dedicate this particular talk to all of you who are trying to push the frontiers of this particular subject ahead. I have had my run, and as I keep saying, every medicine or everything has a shelf life. So you should not push things beyond their shelf life, but start thinking about something new. And that is exactly what this school was sort of basically doing. And if there are some lessons which we can learn from history, that is exactly what we should sort of focus on. And that is the spirit in which I'm sharing these recollections with you. Whenever you talk about a topic of this particular kind, I just want to sort of tell you that I'm just focusing on the legacy in two aspects. The work on source modeling, which happened during this particular period, and the work on gravity wave data analysis, which happened in the same period at IISER. This is essentially the theme which I will sort of expand on. But before I do that, I just want to sort of tell you that when I joined RRI in somewhere around 1980 or something like that, at that particular point, the binary pulsar had already been discovered, and there was a very active pulsar group under Radhakrishnan at RRI. So people who worked in general relativity were trying to look at the observational consequences which you can infer from binary pulsar observations, and one of the persons was Haridas. And I just want to sort of mention this particular paper by him, which sort of tunes with whatever is being talked in this particular workshop. So this was one of the first papers which tried to derive the quadrupole formula using techniques from quantum field theory. A nice summary of all this particular work is in his Vaidya Rai Chaudhary endowment lecture, which I would recommend for you to read. In this particular period, there were some important schools. For example, I had mentioned the school at Karjes in 1986, where Thibaut Damour and Bernard Schutz were lecturers, and both Sanjeev Dhurandhar and I were participants. This was followed by the GR meeting in Stockholm. And then, based on all this, it was realized that in India, we really need to bring the international GR community once in a while, regularly, so that we can follow up trends which happen in the international scene. So the ICGC meetings were set up, and the first meeting happened in 1987 in Goa. And again, you will see that Thibaut Damour, Bernard Schutz, and even Richard Isaacson talked about LIGO in this particular meeting. The fact that ICGC meetings continue every 4 years is a good thing, and we should keep this going, because if you really look at the structure of the ICGC meetings, it basically tries to identify areas where the frontiers are internationally and tries to put the local community in touch with them. So this is an important series of meetings which we should continue to do. Now I come to how I got into gravitational waves. Basically, in the year 89-90, I spent a sabbatical working with Thibaut Damour during this particular period. And this was exactly the period when LIGO was funded. And as soon as it was funded, it was realized that we have the funding, but then we have to focus on what is the most important sources for these particular detectors. Remember that people originally had thought that supernova remnants would be the strongest kind of sources, but it was soon realized that their rates were much smaller, and you did not know much about them to definitely say that a detector like LIGO would be able to see gravitational waves from such sources. And then slowly it emerged that you should really look at coalescing compact binaries of neutron stars as the prototypical sources, and therefore you started focusing on them. Now, when you did that, Kip Thorne basically realized that if you really wanted to look at sources of this particular kind, you cannot see it in the raw data. You'd have to use techniques like match filtering, and therefore you should know what you are sort of looking for. And if you really went to ask the question, what is the sources which LIGO and Virgo will see, then you basically realize that the detectors are sensitive at the required level when the sources are just about to sort of coalesce. So you really need to calculate what happens in the final stages of the inspiral when the system is about to sort of merge. Now, calculating the merger was a very complicated exercise because numerical relativity was not mature enough. But still, a grand challenge program was sort of funded by the NSF to look for the numerical calculation of the final stages. But at that particular stage, if you really wanted to do something analytically, you could only talk about the early stages of inspiral, and that was really what one focused on. So keep realizing the challenge involved, called an international meeting to think about this particular problem, because he realized that you really had to bring in on board any community which is sort of involved in this particular kind of activity. So in this particular meeting, Sanjeev Dhurandhar, I, Luc Blanchet, all of us were participants. And in that meeting, when Kip posed the challenge, Luc Blanchet said that using the formalism which he had developed with Damour in his thesis, you could push the calculations to the accuracy required beyond what was known currently. What was known from the binary pulsar work was the 1 pn correction to the quadrupole radiation. That means beyond the 2.5 pn, you can calculate the 3.5 pn terms. But what you needed was something beyond that. And Luc Blanchet claimed and proved very immediately after the meeting that you could really generalize the formalism which was there in this particular thesis. Then what happened was, since I was visiting Thibaut Damour, Luc Blanchet, Thibaut and myself, we started working on this problem explicitly, and we set up what is today called the BDI formalism, where you go from the source to the final radiative moments via some intermediate quantity which we call canonical moments. And what really helped us do the calculation was the fact that in the context of the binary pulsar, the equation of motion of the binary pulsar of this system was known. You only needed to calculate the flux to that order of accuracy. So the problem of equation of motion was under control, and we had to focus only on the calculation of the radiation. And therefore, using this particular formalism, we could calculate almost within a couple of years what we call today as the 2pn quasi-circular inspiral of a compact binary. This calculation was independently done by Will and Weismann, and the two independent calculations, when they agreed, we knew that you had the analytical formulas to construct the templates which the data analysis people could use to look for gravitational waves in the data which would come out of LIGO. You also sort of realize when you're doing a calculation of this particular order that you really have to know what order of nonlinearities you have to deal with. And in this particular problem, you have to deal with the cubic nonlinearities of Einstein's equation. Now, once this calculation was done, the templates could be used for binary neutron stars. But when you try to apply them for binary black holes, you realize that they were not accurate enough, and therefore you needed to go to the next order. Now, when you did this, you suddenly sort of realize that you are running into some technical complications, because the regularization which you use for point particle approximation, which was the Hadamard method, led to determined coefficients, both in the equation of motion and in the calculation of the flux. And therefore, it really, for almost about a decade, one tried to fudge the regularization to try to see whether you could change the regularization in different ways to get a consistent calculation. It took many years to realize that you really had to come up with something which the people in field theory use, that is dimensional regularization. It was only that method which would give you consistent kind of results. So when this was done in two different approaches, both the ADM approach to calculate the equation of motion and the calculation in the harmonic coordinates by the standard GR kind of methods, both these things led to consistent results. And what you sort of realized was that you really had to look at the calculation very critically, because depending on the order at which you are working, you really had to be careful about the regularization procedure which you use and whether it involved only regularization or even renormalization. It could very well happen in different gauges, you need to do different kind of things. So it almost, originally we thought that in a year's time we would come with the 3PN calculations, but it almost took about 10 years for the next order to be sort of controlled. And while doing that, you basically realize that you calculated the movements which are required not in just 4 dimensions, but in d dimensions. So it required more technical preparation, and once you did that, you had a consistent calculation which you could use to do data analysis. And because of the fact that the hereditary effects, which are the tail effects, were known at the 3.5 PN order, you could sort of extend the 3 PN calculation and have the phasing up to 3.5 PN order. Then after a few years, the group at Muda and at RRI could calculate the waveform also. Calculating the waveform requires more accuracy, because when you calculate the flux, you are calculating the square of the waveform. So you require less post-Newtonian accuracy. But when you calculate the waveform, in some movements you require higher accuracy. But that could be done because you had a consistent formalism to do things. So essentially, you can say that this was a very important breakthrough, because you had what was required to do data analysis. The numerical relativity breakthrough to actually do what happens at the merger happened only in 2005. This was just one of the numerical runs. Till the whole numerical infrastructure could be built to calculate gravitational waves when systems are merging, really took, let's say, at least 5 to 10 years after this. And therefore, it was really important that the formalism which was analytically put together really was available for people doing data analysis. Now, when you look at an approximation scheme, you realize that they break down at some particular point, because of the fact that the parameter which you are using to make the post-Newtonian expansion becomes large, because you're getting close to the horizon, and therefore you're getting close to the velocity of light in some sense. So therefore, you again go back to what high energy physics people do, basically use Pade approximants, for example, to extend the domain of validity of the post-Newtonian expansion. So this was really another idea which Damour had, and with Satyaprakash, we proposed the use of Pade approximants to construct the data analysis, the phasing for various things. Now, once you brought in the Pade approximant, Bonanno and Damour again worked to create what we call as the effective one-body approach, where you generalize what you do in classical mechanics, where you can convert a two-body problem into an effective one-body problem and then do the calculation. So similarly, looking at the two-body results, you try to write it in a form which can be written as an effective one body in an effective metric, and that simplifies but gives you more accuracy, because in the construction of that you can bring in your Pade approximants and go beyond the post-Newtonian calculation. Now, the effective one body approach can be improved even further by improving your construction of the waveforms which you use, and this again was done by Damour, myself and Nagar a few years later, where you try to identify the different physical effects which come in the waveform and deal with each of the physical effects independently rather than in a in a complex multiplied kind of form. So you break the waveform into pieces where each piece represents some physical effect and deal with each physical effect in a separate way by using Pade approximants. So this is the method by which all the waveforms of effective one body are constructed today. The other thing we sort of realize is that when a theoretician makes a calculation and produces a phasing formula or a waveform, when you give it to a data analyst, it is important to tell them what really are the crucial kind of results. So to this end, there was a series of papers put together by Damour, Satyaprakash and myself, where we produced a digested version of the analytical results, which could be relevant for the gravity wave data analysis applications. And this really helped in constructing the detection waveforms and doing parameter estimation subsequently. So the kind of tools which we developed was pointing out that when you are using approximate waveforms, you may be dealing with waveforms which are inequivalent, and therefore your results could be different depending on the family which you used. To measure those things, we introduced notions which we call effectualness, which is the usefulness of your waveform to do detection. Faithfulness, the idea is how good are your waveforms to produce the right parameters of the system. And then when you have frequency dependence in your waveform, you basically cause technical complications if you don't keep control of what are the waveforms what are the window functions you are using to truncate these particular waveforms. The stationary phase approximation is used in calculating the frequency domain waveforms in gravitational wave data analysis, and sometimes you can go beyond the leading order stationary phase approximation. How to do that? Again, we came up with a mathematically complete way of doing these things. So once we wrote this series of papers, basically it allowed you to understand the limitations of your template family in doing gravitational wave data analysis, and this has now become a standard tool to do gravitational wave data analysis. Once all this was available, the students in my group, in collaboration with Satya Prakash, used the accurate waveforms to do problems on what is the implication on parameter estimation, how do you test gravity by using these waveforms. If instead of using the only the frequency domain, only the stationary phase, if you wanted to use the amplitude corrections, what kind of advantages you will have for astrophysics and cosmology, for the future detectors like LISA and the Einstein telescope. All these kind of problems could be addressed by using the waveforms which were constructed to 3.5 pn accuracy. So this basically is what we try to sort of contribute to the community: analytical waveforms and then the data analysis elements coming from those waveforms. There was a theme which my group in RRI focused on, because when you originally look for gravitational waves, you assume that most of the waves are sort of moving in quasi-circular orbits, because by the time they start merging, the system has lost all its eccentricity, even if initially it had eccentricity. So the leading approximation we use is quasi-circular approximation, but we know in astrophysics there are systems which will be quasi-eccentric. So how do you generalize the formalism which was sort of set up to these kind of bodies? Now, the classic work is the work of Peterson-Matthews using the leading quadrupole radiation. So we wanted to generalize it because now we know the equation of motion and the flux to higher orders. So basically, using this, we provided the phasing formula for these eccentric binaries to this high order. And if you really want to do the phasing, in addition to the calculation of the energy, you need to calculate the angular momentum and the angular momentum flux to these orders of accuracy. So once these things are done, you can generalize the quasi-circular phasing to quasi-elliptical phasing, and by using the conservation of energy and angular momentum, you can evaluate how the orbital elements which describe the eccentric system, how the orbital elements will change because energy and angular momentum is being lost to gravitational radiation. This is really the Peterson-Matthews calculation, but generalized to 3 pn. That means to 5.5 pn terms in the equation of motion. Now, this really leads, as I told you, to the secular, that is the long-term evolution of the orbital elements, and therefore you are controlling the equation of motion to order 5.5 pn. Then you can ask the question, can I go beyond the secular evolution? Because remember, in addition to the radiation reaction, there is an orbital time scale involved in this particular problem. So you can do that. You can go beyond the secular evolution by using the standard method of variation of constants. So once you do this, there are post-adiabatic short period contributions to the orbital phasing, and you can calculate them explicitly. And these contributions will affect your gravitational wave polarizations, and therefore analytically you can calculate and go beyond the secular radiation, secular terms in the equation of motion. So finally, that you have all these things required, and therefore in 2019 with colleagues in Switzerland, we could calculate the 3 pn modes for the eccentric case, which involves the tail, the post-adiabatic correction, and the memory effect. And therefore, these results are also now sort of available, and they are important because all the 90 systems which we have detected up till now are supposed to be quasi-circular in quasi-circular motion. And we believe that in the future runs, we may see signatures of an eccentric system. So therefore, since eccentric binaries are the next category of gravitational events which may be discussed, you can call them known unknowns, because we know that systems have eccentricities, but we don't know how much eccentricity they will have. So therefore, if we see an eccentric binary, it will tell us something about the system, astrophysical scenario, which is creating this eccentric binary. So the highlights of this full program, I would say that there is this MPM-PN, which was sort of constructed when Damour and Blanchet extended the work which came up for the coalescing binary neutron star case to calculate 1 pn corrections to the binary pulsar problem. That has been sort of generalized way beyond where it began. And in a sense, one can say it is the most successful one because it can deal with all aspects of the problem. It can deal with the conservative equation of motion. It can calculate the radiation field at infinity. It can calculate all the nonlinear effects related to tails and memory. And over the last 30 years, it has emerged as a consistent algorithmic approach to analytical gravitational wave computations. And if you look at a textbook by Maggiore, you will find that this is exactly the calculational method which is summarized in that particular textbook. If you want to learn more about this particular method, you can look at the living reviews by Blanchet, which has been recently updated to really look at the current status of this particular program. If the 3 PN phasing took 10 years, the next order coming to the 4.5 PN took almost 20 years, because starting 2005, people now try to go to the next order, and then the complications which came at 3 PN were not sufficient to solve this particular problem. Again, technically, if you ask me a one-line summary, what happened at the 3 PN was that the ultraviolet divergences, because of the point particle approximation, needed to be dimensionally regularized. But the infrared terms could be calculated by the Hadamard method. But when you went to the 4 PN, even the infrared divergences needed to be treated by the dimensional regularization. So it added the next level of complication, and therefore, even after doing that, there were additional complications because of the emergence of the tail terms at 4 PN, and therefore, till all those things were sort of taken into control, it really didn't give you the full phasing. So the tour de force of this particular program is the construction of the 4.5 PN for binary systems. So if you ask me, what is the scaffold or the foundation which underlies all the data analysis which happens, it essentially is the MPMPN results and the numerical relativity results. What you really see as the arch of this whole data analysis program is really something which comes from the use of the effective one-body method and another set of template families which are called the phenom families, which was first sort of constructed by Ajit here. This basically constructs in the frequency domain by extending the post-Newtonian results to the regions of final merger. The frequency domain templates, including the late inspiral and the merger. So these two families, which are the basis of all the data analysis which LIGO, Virgo, Kagara does, really comes from the numerical relativity results and the MPMPN results which are produced by the community. And therefore, whether you use it for detection, estimating parameters, or extracting physics by using for testing gravity, all these results really come from all these MPMPN and the numerical relativity foundation. And therefore, it's not a big surprise that in Kip Thorne's Nobel lecture, the MPMPN approach is indeed referred to. Also, as I said, the consequence of this was the PN work, the test of gravity application, and the quasi-normal mode, which was earlier given by Vishweshwara. So all these publications find presence in the discovery paper of the gravitational wave, which happened, as you know, in 2015. In a sense, you can say that all this, the students who really worked at RRI and IUCA basically are part of the community of gravitational wave researchers in India today. And in a sense, all this is the foundation of what really happened in the test of gravity work which happens in the LIGO-Virgo collaboration from India. Essentially, all this work which happened over the past couple of decades really is the foundation which really led to whatever is happening today. I have talked in detail about what I have been sort of involved in, but it is important to realize that exactly in that same period, there was a parallel activity on data analysis in a group around my distinguished colleague Sanjeev Durandar at IUCA. Now, Just as I cut my teeth in the Meudon group under Thibaut Damour and Luc Blanchet, Sanjeev Dhurandhar had connection with the group of Schutz in Cardiff, and this group essentially contributed many fundamental things to gravity wave data analysis starting from 1990. For example, they, with Satya Prakash and students, they set up the fundamental work on setting how do you place templates for doing gravitational wave detection. What is the optimum way of doing this? How do you generalize what you see in a single detector if you have a network of detectors? What is the optimal way of using data from a network of detectors? Do you look for a gravity wave signal at one stroke, or do you look at it in two stages? This is what is called as the hierarchical stages. First you look crudely and then you look finely. So this hierarchical method was developed by this particular group. If you really want to look for the stochastic background, you can adapt things from cosmology and use the radiometer approaches to look for gravitational waves. Again, a group, Sanjeev, Tarun, Sanjeet Mitra, essentially worked on these particular aspects. It's very important to note that the IUCA group was one of the lone groups which collaborated with all international detector groups at one particular period, both bar detectors and interferometric detectors. And therefore, in this period from 2000 to 2010, they were the sole group in the LIGO scientific collaboration from India. So Sanjeev's contribution in integrating the Indian gravity wave community with LIGO scientific collaboration was a remarkable achievement, and what we are today owes much to his foresight in taking on this hard task when he was the only group doing this particular kind of activity. Going ahead, Sanjeev sort of realized that in the future, the space detectors would become relevant, and therefore, together with Archana Pai and Rajesh Nayak, he worked on time delay interferometry aspects for the LISA. So again, you can see that LISA is supposed to come on in 2035, and Sanjeev and his collaborators made fundamental contributions to this, because by generalizing mathematical techniques, you could find out all possible solutions which you could have for this time delay interferometric problem. So it's an interesting mathematical exercise which found very good applications for gravitational wave data analysis. So again, the most important thing one has to keep in mind is in building the gravity wave community, the activity at IUCA played a very crucial role in that same couple of decades. So therefore, it's not surprising that when the discovery paper really came, there were contributions to it from different groups in India. As I said, to the foundations of the field, there was work from Vishu on quasi-normal modes that finds a mention. The work on source modeling, which I told you with the French group, finds mention, and the work on data analysis done by Sanjeev Dhurandhar and Satya Prakash at IUCA finds mention. In addition to that, different problems, different aspects which were sort of looked at in the discovery paper, contributions to that were made by different groups from India, and these are a list of what people contributed to and who are the people who contributed to that. So there was a solid contribution to the discovery paper, but this really happened because of the fact that over 2 decades, already there was a foundation which was laid. It cannot happen overnight, and that is what I would like to sort of stress. Now, you may ask the question, while we are talking about source modeling and data analysis, was there any attempt to start an experimental activity in India? And it's interesting to note that in that particular period, starting 1990, at IUCA, which was just starting out to be a new institute, Sanjeev Dhurandhar, Dadij, with colleagues in RRCAT, which was then called only CAT, Center for Advanced Technology, they put together a kind of proposal to set up a prototype instrument in 2 stages with some financial requirement. Now, this was sort of reviewed, but they finally decided that we didn't have the critical teams to do this, and therefore it was not sort of funded. Now you can see there that even if on a small scale this was sort of funded, in the next 20 years we would have had at least an experimental community which would be sort of built. And just as in the source and data analysis we have a presence, we could have had a presence when things were sort of needed. The other interesting thing is there was a collaboration with Australia. Australia was trying to build its own detector, and David Blair wanted to collaborate with the Center for Advanced Technology to build a vacuum kind of system. Again, a proposal was sort of put together with Raja Rao as being one of the lead contracts at this particular point. But again, history intervened because in 1998, the Pokhran blast came, and subsequently, any collaboration between any foreign country and India was sort of put on the burner for many years. So in projects like these, one should keep in mind that political things also play a role in the realization of these kind of projects. For example, the best team in laser interferometer was from Germany. And they had if you really wanted a proposal, a team which could put together a proposal, it was the German team. So the geodetector was sort of being proposed, but unification happened. And then they decided that they would not go for a big detector, but only build a prototype which is 600 meters. So political decisions affect the realization of high technology and major projects like this. And one should keep in mind that therefore, in addition to what you're sort of doing, you may be sensitive to other things happening around you. So watch out for them. So with that history, something interesting happened in 2009 because IUCA turned 20 because in 1989 it was set up. By 2009 it was at 20, and they were revising their agenda to ask what new areas they should sort of seed in the next decade. So there was a meeting there, and in that particular meeting it was sort of thought that since we had a presence in gravitational wave theory and data analysis, maybe we should try to stretch our feet and get a footprint in experiment. And therefore, the people who were in that particular room essentially decided that they should form a kind of community to seed this, and the Indigo Consortium was really sort of initiated there. And since I was around, I was nominated to be the chair. You didn't have any particular choice. You didn't sign up for the role. You just stood in a line. Everybody moved back. So it looked like you were, taking the leadership there. That's exactly what happened because, as I said, I had no experimental credentials. I was a hardcore theorist, and therefore I had no credibility to be the chair of this particular community. But since somebody had to take it up, I sort of reluctantly signed up to the role. But then interesting things were happening because all the students and postdocs who had grown with us and had gone abroad to work with these detectors started coming back to India exactly during this particular period. So what happened was that at different Indian institutions, people who had worked with the international detector groups really started coming back, and they were part of the Pan-India Indigo group to contribute to the LIGO scientific collaboration. So you can see here at IUCA, these were the two people. At IISER Trivandrum, Archana joined, then Rajesh, Anand Sengupta, Gopu, Ajit, Arun. So the community which is of gravitational waves today essentially came back around this particular time, around 2000, post 2000. So therefore, there was a growth, this group at IUCA, which was the single group, now became a pan-Indian group and started contributing to the LIGO scientific collaboration. So Indigo was a pan-Indian, and it was the Indian presence in the LIGO scientific collaboration. There were about 51 members when we sort of basically started. And then there is something called the Gravitational Wave International Committee, which kinds of oversees the gravitational wave experimental activity globally. So since we were trying to have a footprint in experimental activity, we were invited to become a member of the Gravitational Wave International Community. So Indigo became a member of this body, and then we started exploring collaboration with Australia to help set up their gravity wave detector. Now we realize that this could not be an activity of a single institute in India. We really had to bring scientists from all Indian institutions, because in different Indian institutions there was different technical expertise. All the expertise didn't remain in one particular institute. So therefore, we tried to look for institutions where there was expertise and where there was interest. And initially, for example, IUCA, RRCAT, TIFR, IPR turned out to be these institutions. Their directors were supportive of exploring such a collaboration, and therefore we started exploring our collaboration with Australia. But then, interestingly, globally, something more interesting was happened. The first generation detectors, which was called the initial LIGO, initial Virgo, they achieved their design sensitivity. And then people realized that they had to go to the next level of advanced detectors, which were 10 times more sensitive. Now, the funding required for that is definitely much more. And you need to justify that by being able to deliver more than what you originally promised. That is, originally you had said that you will detect gravitational waves, but only detecting gravitational waves would not give you that level of funding which you basically required. So people realized that they should use their resources more cleverly, and they used the fact that the LIGO project consisted of 2 sites and 3 detectors. And therefore, if the third detector could be moved further away from the US, it would do a benefit to astronomy. And therefore, they came up with the idea that there should be a global network where the third LIGO detector was moved to a place as far as possible, and that was originally Australia. But when LIGO Australia tried to get the funding, they did not receive the required funding. And since we were already a junior partner in this, we were invited to check whether we would be interested in hosting the LIGO detector. And this is exactly what happened in 2011. And therefore, LIGO India was scientifically assessed to be a critical element of the global gravity wave network, because it could do source localization and hence facilitate gravitational wave astronomy. So this proposal is there, 2011, and then we are just waiting for the DAE to take a call on this. And then something interesting happened historically. 2015, gravitational waves were discovered, and as I told you, we had 35 authors on the discovery paper. And then it's again a miracle that something which happened 1.5 billion years ago has an effect on something which happens in India, because 1 week after the gravity wave announcement, detection announcement was made, the LIGO India proposal, which was sitting with DAE for the last 5 years, was sort of in principle approved. And a few weeks later, it was the MOU between the USA NSF and DAE DST was signed. So again, as I said, not just global events, even astronomical events. So if you believe in your astrology, you should include all the binary black holes. Only then you can predict correctly what is going to happen to your proposal. So then, as I said, the project has an in principle approval. the institutions which are going to run it are the RRCAT, DCSCM, which is the organization in DAE which does civil infrastructure and so on, IPR, which has experience in tokamak and therefore experience in vacuum systems, is on board, and IUCA builds the scientific community for the LIGO India kind of project. So now that there is, remember, there is this Indigo consortium and there is the LIGO India project, and there is always a confusion, who is responsible for the gravitational wave research in India. So we basically realized that it's important to link the experimental project and the scientific community together, and that was achieved by changing the Indigo group into what we call today as the LIGO India Scientific Collaboration. So the LIGO India Scientific Collaboration now has about 16 institutions, 112 members, and its PI currently is Archana Pai from IIT Bombay, and I am the co-PI. Remember, we only had the in-principle approval. So again, we are waiting for the formal approval of this particular project. Finally, in April 2023, the formal approval of the DPR was sort of achieved. And that essentially, as I described, is not the end of the story, but it is like climbing Mount Everest. The project is to climb Mount Everest, and at the foothill you set up a base camp. So the base camp has been sort of set up. The hard work still is pending. So I just hope that when IUCA turns 40, we'll have LIGO India actually sort of realized. Now it is important, you'll ask the question, when we originally proposed LIGO India, it was supposed to be active in 2019. So are we still relevant when people are talking about the third generation detectors? So people are already talking about detectors which are 10 times more sensitive compared to the present generation detectors, like Cosmic Explorer in the US, Einstein Telescope in Europe. So when you have such more sensitive instruments, what is the role of LIGO India? Has it become dated or does it play an important role? Now, the NSF wanted a very precise answer to this particular question, and they set up a team to look into this particular question, which was looked at by a group which included Satya Prakash from the Penn State, and they have assessed that when you look at the scientific returns, even in the generation when you have the third generation detectors, LIGO India can play a critical role because it is a clone of LIGO, but the detectors which are there in the US would be older detectors and they may want to decommission them, and they are also close to the other detectors in the US. So we would be like a LIGO detector but far away. So therefore, when you assess the scientific cases, even in the context of the third generation detectors, LIGO India can play a critical role. So my summary here is in the next generation detectors which will happen post 2035, these detectors will be 10 times more sensitive, but they will cost billions of dollars instead of millions of dollars. And they must bring significant scientific returns to a larger variety of communities, only then it will be funded. It cannot be funded for only astrophysicists and lab gravity wave detectors. Therefore, meetings like the present one, where you look at the gravity waves in the context of other communities, really will play a critical role in the future of realizing these particular detectors. So therefore, I recommend that you regularly meet once in 2 years or once in a year to explore themes like the one which has been explored in this particular meeting. Now we also sort of realize that the formal integration which we have currently of the LIGO, Virgo and Kagra collaborations needs to be made more strong. So therefore, currently work is in progress to have a more formal structure which is being called the International Gravity Wave Network. So the current structure which is there is going to be replaced by something more tightly linked. And again, therefore, you can see that when this is happening, as a community in India also, we should be integrated more strongly and more closely. Only then we will be a valid member of a collaboration of this particular kind. I think I have run out of time, but let me go through this particular slide. When I began my work, on my room, there used to be the Nobel Prize poster of the Hulse-Taylor. And I would explain that how the Hulse-Taylor is the end of one endeavor, but the beginning of another endeavor. And that's exactly what happened. In 2015, gravitational waves were discovered, and the source was a binary black hole. So this is how the subject basically developed, and therefore there is an organic link between what happens in one area of astrophysics and the other. Theoretically, I told you that MPM-PN work happened, but other work happened, like, for example, work on the perturbation way of calculating gravitational waves, self-force approach, and more recently, the field theory method to calculate gravitational waves. We really need communities of that particular kind in the country. We also tried to set up numerical relativity in India, but in spite of serious activity by postdocs, the activity did not take off for different reasons. And it's only recently that at IUCA we have a faculty member, Prayush Kumar, who's a hardcore numerical relativist. So again, we really need to grow this community because it's not enough to have just one person working on the numerical calculation of gravitational waves. So if you really ask, if you really want to make an impact on a particular field, you need to catch it before before it becomes hot. You cannot do it when it becomes hot. And therefore, you need to seed someone actively working in these areas if you want to seed new areas. As I had showed you, Sanjeev and I got into this particular area at the right time. So it is the idea of a the right activity and the right time you have to pick out, but you also have to find the right person, because without a particular face, you cannot really see the activity grow, as happened in the case of numerical relativity. We couldn't find the face for numerical relativity at that particular time, and that is part of the reason. The same thing happened with the experimental part. We should have found a face for the new experimental part at that particular time. So that is also required. So you can see here that LIGO India really happened because of the fact that at 2007 at ICGC, Rana Adhikari was there, and he said, "Why don't you think about a gravity wave detector in India?" Immediately in that same period, David Blair wrote to me, "Why don't you collaborate with us on an Australian detector?" And even though it seemed remote, we decided to go ahead with our collaboration with Australia. So one has to keep in mind that opportunities come very rarely, but when they come, you should be ready to grab them. You cannot let go of an opportunity when it comes to you, and therefore it is important that if you, but again, keep in mind that these are necessary but not sufficient, because we know that many other things can interfere with various things. So I would say that I just want to leave with what is the future of Indigo. So now the fact that the aim of Indigo was to approve LIGO India, now its role really comes to an end. If you look at the acronym, it has been like a chameleon. Originally, we wanted an Indian detector, so it meant Indian Interferometric Gravitational Wave Observatory. Then when we were collaborating with the Australians, we decided to change it to this. And now some people are talking about a decimeter gravitational wave observatory. So they could equally well take our name and call the indigo. But an important other alternative is to re-engineer the indigo so that it is the Indian equivalent of GWIC, because we have currently activity in LIGO related activities, we have pulsar timing related activities. People are talking about setting up some decihertz gravitational wave activity. Maybe somebody will start contributing to LISA analysis. So there is going to be different kinds of gravity wave activity in India. So having a community which will jointly represent them could be the future of the indigo. So this is something which I want people to think about, that think about a couple of members from each of these activities and set it up. But what you really need is a new dynamic chairperson to run this particular activity. So if you can find a chairperson to run this particular activity, I think this is a good way to change what indigo was to what indigo can become. With that, I end my long talk. Sorry for extending, but 30 years in 45 minutes is a challenge. Thank you very much.
Thank you, Bala, for this very unique perspective on history and future also. We are running a bit late on time, but maybe we could take one question if there is one. Okay, I think now it's...
Yeah, as I said, when there is pin drop silence, it means one of the two things. Either it has gone above, so you have ducked, or you have observed everything, which is, or you have observed something. But as I said, the whole thing is that the future is not what this story is. The future is what you are going to write in the next 5 years and in the next 10 years. And I just want you to go with a message that gravitational waves is going to be an integral part of whatever physics you do, which is why CERN is interested in gravitational wave activity. So if you look at CERN, it has extended itself to looking at gravitational waves because the technologies involved in the accelerators and in the gravitational wave things are very similar. So one can try to build a joint kind of community, and therefore we are all tied together whether we like it or not.
So, hi. Okay, again, I have many questions, but I was wondering, so something we often don't hear about is what's happening on the Chinese front, because even within the GWIC meetings, which by the way are public to all,
the word
on the Chinese contribution, because there are very, very big plans.
Yeah, you're very right.
Something is the Indian gravitational wave community going to get in touch with the Chinese gravitational wave community? Are we looking at partnerships with them as well? Because this is something I fail to see elsewhere as well.
So the problem, as I told you, is in addition to the scientific validity of this, we are influenced by political decisions, and therefore that becomes a bigger hurdle to deal with. So scientifically, we are aware, for example, that China is interested in the space detection of gravitational waves. Because of its fast telescope, it is going to play a very important role in pulsar timing array kind of related activities. Now they even have scientific people from China going back. There is scientific activity happening in ground-based detector related science, etc. But the problem with formally setting up a collaboration with Chinese is most of the time a political thing. So that is something which is beyond our pay scale, and therefore it becomes very difficult to deal with it. But one should try to at least make sure that there is an academic exchange. So the only way the gravity wave community in the US could link with the Russian community was because Kip Thorne used to go between the group in Russia and the group in the US. So some of you who have these kind of personal links should keep the academic thing alive at least, so that when the time becomes ripe and political situations becomes better, the collaboration can start more actively. That would be my personal take on this.
Thank you, Bala. So let's end the session now. And